In this video, we'll explore the reaction of sulfur nucleophiles with aldehydes and ketones. And we're going to see that this is much the same as with oxygen nucleophiles. We're going to be able to make the sulfur equivalent of an acetal or a ketal, which is called a thioacetal or thioketal. The mechanism is exactly the same for acetal or ketal formation, except we have a sulfur instead of an oxygen. Everything else is the same. So we don't need to go over it again. But what's special about these thioacetals and thioketals is they do a couple of interesting things. First off, when we treat a particular aldehyde or ketone, let's go ahead and just put some R groups here. When we treat this with 1,3-dithiopropane, I guess we'll need a carbonyl, don't we? And some catalytic acid, can even be a Lewis acid, doesn't even need to be a Bronsted acid, but we end up with the following. And so just like before with the cyclic ketals or acetals, right, we can make this, use the same molecule. And what's interesting with this is if we treat this with rainy nickel and hydrogen gas, we eliminate it. So first thing we can do is get rid of it. So that's three things now we can use to get rid of carbonyls. We can use the Clemenson in acidic conditions, we can use the Wolff-Kishner in basic conditions, or we can use the sulfur here. Make the dithiane, it might be called, or the thioacetal thioketal with rainy nickel and hydrogen gas. So as long as there's no other reducible component in your reaction. It's neither acidic nor basic, so you have neutral conditions. I mean, slightly acidic for the first step, but most things can handle slight acidity. As long as you don't have any of the reducible components in your molecule, you can get rid of your carbonyl this way. And so you can selectively remove a particular carbonyl using this rainy nickel and hydrogen gas. So, cool things. But it gets even cooler when we have aldehydes involved. If we do the same thing with an aldehyde, and I'll just put a carbon here. So we have an actual molecule. Right, once we've got this, yes, we could do the same thing and remove, we could treat this with hydrogen and rainy nickel and remove it. But we'll be able to do something much more interesting with this. It turns out, what a fascinating reaction. This is called the Seebach reaction. Umpalung means kind of like inverse. And we'll see what we mean with that. So if you treat this with some sort of strong base, for example, butyllithium, butyllithium is essentially it's an carbanion with a lithium positive charge there to stabilize it. It goes ahead and grabs that on there. That was our aldehyde proton, leaving us with a carbanion stabilized by those sulfurs. And this is something that's only in the case with sulfur. We can't do it with the oxygen analog, only with the sulfur one. So we have this carbanion now, and that carbanion is just ready to go. It wants to do something. And we're going to see that we can actually put any manner of electrophiles with this. Alkyl halides, other carbonyls, whatever we like, some sort of electrophile, and this will act as a nucleophile and attack it. So essentially, what this really is, because we can remove the sulfur later. What really this is it's a nucleophilic carbonyl carbon. And that's where this Oompa idea comes in. I just like saying that. That's the real reason for this reaction, right? Is now we have a nucleophilic aldehyde, which is really strange, isn't it? But that opens up the door to all manner of synthetic utility. And so if we put in some electrophile, I'm going to just say E+, we can nitrate things, we can alkylate things, we can acylate things, we can do all sorts of fun stuff. So I'm going to just put generic electrophile for now. What can happen is we can go ahead and attack that electrophile. And in doing so, we now have our electrophile bound to what used to be the carbonyl carbon. And we still have those sulfurs there. Now, of course, if you were so inclined, you could use your Raney nickel and get rid of that if you don't need the carbonyl back again. So if you want to use Raney nickel and the hydrogen, go ahead. You have your electrophile now attached on. So if that's your goal, that's great. But treat this with mercury too and water, and you get your carbonyl back. So we can use these sulfur bits as a way of kind of shielding, I don't want to say blocking or shielding or protecting, but we can kind of mask our carbonyl, hide it, convince it to become a nucleophile, and all of a sudden we have a nucleophilic carbonyl to which we can attach an electrophile. And again, electrophiles can be things like alkyl halides, so if we need to put an alkyl group, if it's an acyl chloride, we can do that. Add another aldehyde or something on, we can do that too. So lots of fun synthetic utility here. So you can form any this way. So fun stuff there. Let's take a look at just a couple of examples. So let's say I have benzaldehyde, and I want to make this benzaldehyde into, what shall we make it into? Let's have something like this. Or in fact, let's even get rid of this one. Let's make it into that. You might think, well, what? How bizarre. But we can do it using these sulfur nucleophiles. So what we want to do is remember that these sulfur nucleophiles turn an aldehyde into a nucleophile. So by converting this into the sulfur, apparently only 2 carbons this time, doesn't really matter, but here we go. Usually we would prefer the 6-membered ring, but apparently I'm making the 5-membered ring today. So we have our sulfur there. What we can do is, again, we use the butyl lithium. We'll turn this into our nucleophile now. Again, this time we only have 2 carbons in between. That's just by random choice. We have our lithium. And now we think, okay, well, we're adding 3 carbons, and one of them has a carbonyl on it. So what should jump into your mind is acyl chloride. And so with this acyl chloride, we're going to probably want something with 3 carbons, so that would work. And in this case, we're going to go ahead and, just like with the the electrophilic aromatic substitution, we're going to go ahead and, I guess this is technically slightly ahead because we haven't covered acid chlorides yet, but what happens is we're going to pop open that carbonyl. And I'm just doing the mechanism right now just to help us see how we get this product. But in an example of how synthetically useful this reaction is. Move that arrow. All right, so now we have attacked our carbonyl. So we have that minus charge, we have the chloride, and then the other two carbons. And we have a leaving group already in this molecule, so down it comes, kicks off the chlorine. And now we're left with our ketone. And then we have the sulfur bit. And so we have options. We can remove it. Well, since we already have what we want to get rid of it, we should go ahead and use our rainy nickel. If we use our rainy nickel, we will probably also reduce the ketone, but that's okay. We can work with that. Once we reduce that ketone there, so we're going to get rid of that the sulfurs, right? Because that's what the rainy nickel does. We're going to probably have an alcohol here, which is just fine. Because remember, we can reduce ketones with hydrogen. That would work. And then if we need the ketone back again, we can just oxidize this. Be careful about your oxidant choice. You want to probably use a mild one because KMNO4 will cleave that carbon, remember, and make the carboxylic acid. But so something like a DMP or SWERN or any of our other mild oxidants will get this back to the ketone without worrying about that benzoic position. So crazy stuff we can do. Electrophiles can be acyl chlorides, alkyl halides, nitros. Remember we had that the nitric acid and sulfuric acid to make the nitronium ion as an electrophile. Aldehydes, ketones, we can attack those as well. So we have all sorts of different options here. So with this reaction, very synthetically useful, very cool reaction. So kind of hard to see where it's shown up, but we have a lot of options with it. So just keep it in mind for your synthesis toolkit. We have a couple more nucleophiles still left in this chapter. We're going to take a look at hydrogen nucleophiles and then finally carbon nucleophiles. And then we'll be done.